We present Mesh Classification with Dilated Mesh Convolutions. Accepted in ICIP 2021. In this paper, we establish a notion of dilated neighborhoods to perform dilated convolutions on 3D triangular meshes. Based on this notion, we design our novel dilated mesh convolution block to perform deep learning tasks. In particular, we perform shape classification of meshes in the ModelNet 40 and 3D Future datasets. In computer graphics, the most popular representation for 3D shapes is the polygonal mesh. Triangular meshes provide a natural delineation of complex 3D shapes with arbitrary topologies by piecewise triangular representations. Large flat surfaces are faithfully represented with a few large triangles. In more intricate regions, a large number of triangles can portray the underlying surface. Directly using mesh elements for shape analysis tasks in deep learning frameworks is non-trivial. Meshes are irregular. This irregularity is a virtue of the varying number of mesh elements with arbitrary permutations. Meshes also consist of multiple elements, and different types of connections may be defined among them. For example, a unit to a deep neural network can either be the faces or edges of a mesh, and different connections can be defined among them. Among the deep learning methods, convolution neural networks flourish in reasoning about images. The convolutional layer in CNNs detects local conjunctions of features by applying the convolutional operator on the previous layers. In tasks requiring dense predictions, dilated convolutions are popular. Dilated convolutions upsample a convolution kernel by inserting holes between its kernel elements. Applying convolutions on images is trivial since they are densely and uniformly sampled on a grid. However, extending the dilated convolution operation to meshes is non-trivial since meshes are irregular. Initial work supplied regular CNNs to irregular 3D shapes by projecting the shapes to multiple 2D images or volumetric grids. However, these methods are slower, resource-intensive, and lose geometric information. Many methods have successfully applied CNNs to irregular point clouds by defining neighborhoods for convolution through k-nearest neighbors, ballpoint queries, etc. However, point clouds are inherently oblivious to the local surface of a shape. More recently, a few methods have successfully applied specialized convolutional operators tailored to exploit the geometric properties of meshes. Among the shape analysis method applied directly to meshes, MeshNet is a pioneer in classifying meshes in a deep learning framework. MeshNet's mesh convolution block applies the convolutions directly on meshes. In their work, the faces of a mesh are like pixels in an image. Neighborhood for convolution around a face is defined by faces immediately neighboring it. This, however, limits the receptive field for the faces. We build upon the mesh convolution block to perform dilated mesh convolutions. Below we illustrate how to make different ring neighbors around a face. We use the terms face neighborhood with a dilation rate and ring neighbors interchangeably. The first neighbors of a face are a set of faces connected to it by an edge. The second ring neighbors of a face are a set of faces sharing a common edge with its first ring neighbor. Note that faces in the previous rings are omitted from the second ring neighbors. The approach is extensible to obtain the third ring neighbors and more. Once the dilated neighborhoods are defined, we gather features at the rings. Ring sampling is the process of querying features from ring neighbors around a face. Our ring subsampling layer subsets feature at a ring neighbor with a sampling rate S as shown. The main contribution of our work is the stack dilated mesh convolution block, which is designed as illustrated. Features are either sampled or subsampled from different ring neighborhoods and are refined by passing them through the convolutional layers. Feature aggregation is performed for the different ring neighbors by max pooling. Finally, features from the output of different dilation rates are stacked to produce a multi-scale response. We adapt MeshNet to perform dilated convolutions by replacing our stack dilated mesh convolution block in place of its mesh convolution block. We compare our approach against the baseline MeshNet for classifying meshes in the 3D Future and ModelNet 40 datasets for experimental validation. Dilated convolutions improve the performance of the MeshNet model and yields accuracies competitive to other methods. We also investigated the role of different ring neighbors and subsampling rates in SDMC. Improvements in MeshNet are observed for almost all ring neighbor configurations. It is evident that classification accuracy increased when third ring neighbors are utilized in a standalone manner or in combination with other ring neighbors. When no rings were used, accuracy drops are observed. We also observed that the classification accuracy starts to plummet with an increase in the subsampling rate. A similar phenomenon can be observed on the 3D future dataset. Again, multi-scale SDMC with a wider receptive field gave the best results. Subsampling was beneficial on both datasets, and a subsampling rate of 0.33 gave the highest classification results. We defined a notion of face neighbors with dilation rates to perform dilated convolution on 3D meshes. We proposed the novel stacked dilated mesh convolution block to summarize spatial region around mesh faces at multiple scales. By incorporating SDMC into MeshNet, we improved its performance. Dilated mesh convolutions can benefit further studies on more complex 3D mesh applications.